Welcome everyone to our webinar. First of all, a few organizational things for you to know. So your microphones are muted during the webinar, so you cannot directly talk. So in case you have any questions, please use the questions box, the Q&A section, and we will answer your questions after the webinar, at the end of the webinar. And also, please be aware that this webinar is recorded. So what is our webinar about? It's about solving recurring process issues faster with AI-driven root cause analysis at smart factories. And we are two presenters. So before I introduce myself, Jürgen, could you please introduce yourself?
Yeah, hello, thanks for having me. My name is Jürgen Käser. I'm working at Voith. We'll talk about the company in a bit. In my current role, I'm responsible for the development of process optimization solutions, everything from classic model predictive controls to advanced solutions using artificial intelligence, and Vernaio being one of our suppliers, currently our main supplier for AI technology. I'm happy to give you some insights in what we're doing with what the guys are providing.
Thank you, Jürgen. So my name is Robert Meißner. I'm a co-founder and head of solutions at Vernaio. I'm very happy to have Jürgen here in this webinar, and also happy to have you all joining us, and that we have so many interested people here today. So this webinar will have two main sections. So the first thing is that I will give you an introduction. So we will talk about recurring process disruptions and how we can treat them with AI. So what is the approach to treat them with AI? Kind of the theoretical presentation. And then I will hand over to Jürgen, who will then demonstrate how he has done this for Voith with a real case in the paper industry, in the paper making process. And I will take about 30 minutes, and then I think Jürgen will also take 30-40 minutes. So we should have sufficient time for everything. All right, then let's jump right into it. So first of all, the setup or the challenge. So what is this all about? Where are the problems coming from that we want to solve? So we're basically in complex production environments. We have complex production lines like or production assets, for example, in steel making, in paper making, but also, let's say, in bottle filling or mining or all kinds of different industries and process industries. And so what do they all have in common? They have in common that we have complex cause-effect relationships, meaning that the cause and the effect can be pretty far apart from each other. So I would say if the problems are not complex and simple to solve, then you just solve them. So of course, we are focusing on the more complex ones. And as an example, Jürgen, correct me if I'm wrong, but in paper, sometimes you have the cause 2 hours before the effect. So it's really important to have an overall look at such complex processes as much as possible. So the second thing they have in common is we have hundreds, sometimes thousands of process parameters. For example, a signal, sensor data, it's all raw data that is available. And this data it's basically a treasure because there is a lot of answers to what is happening are in the data. So there's a lot of information in the data that is very useful, but we have not necessarily an easy or efficient way to get the required insights out of this data. And this is the result of that is that we have a lack of process transparency. And this means that we have unintentional side effects usually that are just hard to control because they're hard to understand. And this leads us directly to the problem itself. So the challenge leads us to the problem that we have those unintentional recurring side effects that are basically damaging our performance and our quality. So you can see here the OEE, or the overall equipment effectiveness. I'm sure that many of you know it. It's one of the most common KPIs to measure the efficiency of production lines and assets. And you can also see here we have different areas. So everything beyond 85% is considered world class. And to be honest, or to be real, 100% is usually not achievable because we have just availability issues caused with the plant downtimes, maintenance, setup, and so on. But anyway, if you are beyond 85%, it's considered world class. Between 60 and 85% is good. Between 40 and 60% is average. And beyond 40 is considered a poor OEE. Of course, this differs from industry to industry, from production line to production line. For some, it's harder, and maybe they're already great if they achieve 50%, and for others, maybe they can really reach up to the 80s or even 90s. And it just depends. Anyway, so what is the OEE made of? What is the OEE really measuring? So it's measuring three things. The first of them is the performance. So the performance itself might be damaged with micro stops and slowdowns, just the recurring things that are happening. So, and if the performance, of course, is not 100%, but it's a 70%, then the OEE can already not go beyond this performance. Next thing is the quality, which is also can also lower our OEE, and usually does. So if it further lowers the OEE, then it can at maximum be here at like 55% or something. And then we have, of course, availability, which we also want to mention here, which further lowers the OEE. And in the end, all three together influence the OEE, and this is what the real OEE is. And today we want to focus mainly on performance and quality, and not so much on availability. So availability is usually addressed by condition monitoring and by or anomaly detection, predictive maintenance. But this is, from our perspective, this is already, there are a lot of solutions for that. But on the other side, performance and quality, so really in the process itself, is not tackled so much right now with AI. So the baseline is we have recurring process disruptions and inefficiencies. So I will tell you on the next slide what exactly I mean with that. And the thing is that just a low OEE always means that we have increasing costs. It means that we use probably more material than we need to, that we have more energy consumption, we have more CO2 emissions, we have, of course, a lower quality than we want. So all this is, negative influence on our OEE, and this is always increasing the costs. So let me start at this point, the first poll, where I want to ask you if you know about the OEE of your production lines, if you have some and you think that the OEE could be significantly higher than it is. So I started right now. So you should all be able now to see the question, and I will wait a minute. All right, so people have voted, so I will close the poll, and you can see the results. So interestingly, that many of you think, or most of you think, that the OEE could be significantly higher. Only one person thinks that it's already high enough, and some of you don't know. So thank you very much for your feedback. So let's go on. What are those recurring process disruptions and inefficiencies? Looking at different production lines and production assets, we just have different kinds of recurring disruptions. You can see here on the left, we have steel making, paper making, bottle filling, tobacco lines. So it's really various different production lines. So common recurring disruptions are, for example, breaks and cracks. So in steel making, when we have a hot rolling or a cold rolling, there can just be cracks in the material. There can breaks in the material, which is dangerous. Of course, we have in the paper making lines, we have the paper break, which is a breakage of the paper web during the production, which is causing a great mess and has to be cleaned up. We have in general micro stops and slowdowns that are just damaging our performance, whatever may cause them. We have things like overcooking, as you can see here very impressively on the right. This is a steel making disruption called slopping of slag. It's basically an overcooking of this vessel, which is also very disruptive. We have in general jams and shortages that might be very hard to predict. We have things like torque peaks at engines or something that are damaging the equipment. Or we have in general just deviations and drops of important KPIs. So you could also say we have a KPI like a moisture or a quality, and it just drops for some reason over a certain period of time below a value, before a certain threshold. And this is also a disruption or an inefficiency that is occurring. And what those recurring disruptions usually have in common is they seem to occur just out of the blue. And obviously, I mean, nothing just occurs out of the blue, but for us, looking at the process, why are they so hard to control? Because they seem to occur out of the blue, and this means they leave insufficient time to counteract and prevent. So in the steel case, I only can see a few seconds before I see that the whole thing gets brighter, and then it's already too late. Then the slopping is already happening, and it's there is no time to apply countermeasures. So if I only had known earlier, then I could have done something. And this is, of course, let's say a great starting point. So because we have all this data, so let's have a look at the data perspective of a disruption, which just looks different than our own perspective on the disruption. So in the data perspective, the disruption itself is basically just the tip of the iceberg, as you can see here on the right. So we have here a signal. This is an important kind of signal. It's a Boolean signal, or it's called a 0-1 signal. And this signal, as you can see here, so over time, it is 0 if the disruption is not here. So let's say the paper break is not here, or the slopping is not. And then it's certainly 1, means the disruption is here. Oh, I just was reminded that we had another poll. I forgot. So please let me just quickly go back and start a poll, because I want to know a little bit more about one thing. So about recurring process disruptions. So the question here is, if you know about those recurring process issues or disruptions that pose a significant challenge to the production line or to the OEE. So meaning if you have concrete recurring process disruptions that you have in mind that should be addressed. All right, thank you very much. I will close the poll and show you the results. So as you can see, we have at least 4 of you know about real recurring disruptions, and only some not. So this is interesting. Thank you for your feedback. And now let's go back to the presentation and to the 0-1 disruption signal. So this is just for treating such a disruption with AI. This is a great starting point to have such a Boolean signal. It is a Boolean signal that just tells us over time when is the disruption present and when is it not present. Because then the AI can just look what, let's say, other signals do during this time, but we will come back to this later. So the disruption itself is just the tip of the iceberg. And during this time where the disruption is present, I mean, the process is obviously not okay. So we obviously have a problem and we don't need AI to tell us this. It's just clear. But then, since the disruption usually doesn't just occur out of the blue, but has a build-up phase. And this build-up phase is more or less hidden, as you can see, compared to the iceberg. So the whole build-up phase is somehow underwater. We might know a little bit about it, but not too much. And it's basically hidden. And this makes it so hard to grab. And this means that we have a significant duration or time during the process where we still think things are okay. It seems okay, but actually it's not. Because during this hidden build-up phase, we have just some characteristic unhealthy behavior. So basically, starting from the okay phase, at some point, our whole process changed from I'm okay into I'm now slowly building up some unhealthy behavior that in the end results into this disruption. And so this build-up phase is the thing that we really need to figure out and understand. Because if the disruption is already there, then it's too late to do something. We can just clean up and then go on. But in the build-up phase, if we could apply countermeasures soon enough, somewhere here in the middle, then we might be able to lower the risk and to counteract this unhealthy behavior and get the process back into a healthy state before the disruption occurs. And this is, after all, of course, the goal, what we need to achieve. So we want to identify the characteristic unhealthy behavior, which, by the way, we call a fingerprint. And the fingerprint is basically how the process interacts, how different things work together over time in the build-up phase, which then leads to the disruption. And the great thing is, as soon as we have the fingerprint, we are basically almost done with solving the problem, because the fingerprint lets us usually understand what is happening. So it's shining light on this build-up phase. I can see what is happening, how things work together. Then this fingerprint also gives me the opportunity to predict. I can basically build a risk signal. If I can measure, if I know this behavior, then I can measure it, and then I can create a risk model that is just telling me already here that the risk is now rising and rising until to the point where the disruption really happens. And then in the end, if I have a countermeasure, of course, I can prevent the disruption. After all, we don't just want to understand and predict. In the end, we need to prevent really positively influence our OEE and the performance and the quality of the process. So it's the fingerprints that we want to have. And so what does such a fingerprint look like? So we need to have a look into the historical process data for this. So it's not enough, let's say, to look at the live data. Let's say we now need to look at the last 3 months, 6 months, year of data and analyze this historical data. You can see here we have again a timeline, and we have on the left signals, signal 1, signal 2, signal 3, up to signal n. As we know, this might be even hundreds or thousands of signals. And all those signals are behaving in a certain way over time. And what we are really interested in is now looking at those points in time where the disruption suddenly occurred. Meaning we have this point in time where the disruption event takes place. And what we are really interested in is in pattern in this area. So is there some information hidden before the disrupting event, and not just one event? We need to look at all the occurrences of the disruption in the past. Let's say we have in 3 months or 4 months, we had like 200 occurrences or 500 occurrences. Then we want to analyze all the signals prior to those occurrences and see what do they have in common. Where's this characteristic unhealthy behavior? And this is, of course, actually a very hard thing to do. I mean, it might seem very logical to do this, but it's also a very hard thing to do because we have a lot of process parameters. So let's say we have not only like 15 here, but we have 500. Then the question is already, do I really have to look into all 500 signals and all occurrences, or can I just skip most of them because they do not contain relevant information? And the other thing is that we have those complex cause-effect relationships. So you can see here, something is happening here in signal 1, then directly afterwards, something is happening in signal 12, and then in signal 10. And all this is somehow plays together. This is why we call this a fingerprint. So basically every disruption has its own fingerprint. And the third big challenge here is that multiple fingerprints usually are mixed or meshed together. So meaning that I don't have only to look out for some certain characteristic unhealthy behavior, but there might be multiple. And sometimes it was one characteristic and another occurrence, it was another characteristic. So you can already see this is hard to do. But nevertheless, it is doable in a conventional approach. So it can be done manually. But let's say this really requires a substantial amount of domain expertise and pre-knowledge. Of course, it's also a huge manual effort, but the most important thing is that we already know things. Because if we don't know things, then it's basically impossible to do this in a manual way. If we already know things, then we know already which signals might be relevant and which can I skip for a certain effect. So so which signals can I just leave out because I just know that this pressure on this device has nothing to do with the problem, or a certain temperature or whatever. I just know it's so far away, it can't really have something to do with the problem. And this is all pre-knowledge that we can use to then just only look at a few signals. The signals that we know for sure are relevant to the process. But then again, we have to see, okay, this signal 1 might be some temperature. So we need to find some anomalies. We need to figure out, is it somehow behaving weird before the disruptions? And can I find a pattern over all the occurrences? Yeah, and it's just hard. It is a high manual effort. It is done here and there, but it's not done very often. And the worst thing is basically that we are very biased because we are putting in our domain knowledge to figure out patterns. And this means that patterns that are not somehow correlated to the knowledge that we already have, we most probably won't find. And this means we have a bias. And this means also that we probably will cut off information that might be useful to really understand the big picture. So if I know that only 10 signals are relevant, but basically there are more signals that are somehow with such a complex cause-effect relationship are also important, then yeah, it is unlucky to cut them off. But of course, in a manual approach, you have to somehow do this. And in the worst case, you basically just reproduce what you already know. So you don't gain any new knowledge. And so you don't get new perspectives of your problem on a problem. And so you might not be able to solve the problem after all. And the question is then, of course, is there a more efficient way to do this? Is there a simpler way, an efficient way to figure out those fingerprints? And I mean, you might already suggest that is, of course, there is a way, and it is AI that can help us here. So AI-driven root cause analysis makes it possible to figure out those fingerprints automated, but it's not just any AI that you need. So the AI requires special capabilities. And by the way, this is the only slide. I will talk a little bit about AI, but it's important for you to understand that we have certain requirements for this AI to be able to solve our problem. So first of all, it needs to be able to work on raw and unlabeled data, because the labeling, basically finding those fingerprints, is labeling the data. And when we have those labels, as you know, you can predict, we can understand, we can do everything, but we don't have the labeled data. We are prior to the fingerprints, so we need the AI to be able to just look at raw, unlabeled process data and find patterns in there. Second thing is the AI needs to be independent of prior domain knowledge injection. So what we don't want to do is to, let's say, start with a general, with some AI and then put a lot of rules and pre-knowledge into it, because this already, again, creates a huge bias and it's a huge manual effort. So this should not be necessary. And the third thing is the AI should actually be able to do the data filtering itself. So from all those signals that we are seeing here, those hundreds or thousands of signals, wouldn't it be great if I don't have to tell this signal is relevant, this signal is not relevant, this is relevant? So wouldn't it be nice if the AI could just figure out which of the signals are relevant to my problem and which are not? Why should I do this? I might cut off something, especially again in the complex cause-effect relationships. I might just cut something off that is important. So, and conventional AI, like neural networks, just can't help you there because it requires labeled data. So as an example, if you want to train a neural network what a cat looks like, to recognize a cat on an image, you have to show it a lot of cats. And at some point, it has learned what a cat looks like, and it can recognize a cat on an image, but then nothing more has happened that the AI itself has created this fingerprint that we're talking about. So it has the fingerprint of a cat now trained and in the model, and then it can recognize cats. But as we said, we don't have labeled data. We have nothing to train on. So there are no cat images yet. And the solution is that you need an AI that is self-supervising, that is using self-supervised learning, because self-supervised means that it's basically creating its own labels. And this means that it can just fulfill our requirements. And an example for that is our own AI, IVIS, that is exactly doing this. It's using self-supervised learning based on stochastic differential geometry. It's an own approach of ours, but it's self-supervised learning, and this is why it's able to do this very efficiently. And compared to the conventional approach, so let's say that the conventional approach is usually that you first of all, you try to create a model, you try to train a model with the data, and then in the end, when it's trained and you know that the important things are in the model, then you ask the model, what did you find? What was important? Which signals are important and which are not important? And this is basically identifying the root causes. And from a self-supervised learning perspective, this is just not very effective. This is commonly done, but basically it's the wrong way, because first you create the model, you train the model, and then you figure out what has the model learned. And it's very hard to get this information out of the model. But what we need here in industrial applications is real understanding of things. We need as much transparency as possible to be able to understand what's happening and then to prevent it. And so the much more efficient ways to actually do it vice versa, the other way around. First, analyzing the data towards the problem that we want to solve, figure out those fingerprints with self-supervised learning. And then if we want, we can create a model from that, a model that, for example, predicts the current risk of the fingerprint. And this is much more efficient, and this offers a lot of benefits, and it's more transparent. And if we can do this with our AI, then it's much simpler to handle this problem, because the AI finds out the fingerprints automatically. And it finds all the different fingerprints that are somehow meshed together. And it does so just from raw, unfiltered, and unlabeled process data. And in the end, this is of course what we want, because let's say not every one of us is a data scientist, and not every one of us has a lot of time to do this with data. So what we basically want, especially is let's say a process engineer or someone responsible for quality, we want to put in all the data that we have. We want to define, this is our problem. This is our quality that may not go beyond 2 or not be lower than 1, whatever our disruption, our Boolean signal looks like. And then we want to get our fingerprints, to really prevent the thing from happening. The benefits are obvious here. So low manual effort. We are unbiased because we have not used any prior domain knowledge. We have just looked for patterns, and then those patterns are presented to the user, to the engineer, and the engineer can then say, oh yeah, what you found there is basically a cat, but the AI doesn't need to know that. And this is a highly efficient and scalable way to do this. And so after all, what does such a fingerprint now look like in reality? We have seen this picture of the slopping of steel. And basically here on the left, you can see what such a fingerprint looks like. So this fingerprint is telling us a story. It's telling us the story about how the slopping builds up over time before it happens, for us to really understand. So you can see here, I will not go into details, but you can see here like a green chart and a red chart, and you can see this reddish line here. I will if you use my laser point, you can see such a red line, which is when the disruption usually occurs. And we can see that many of those signals already start behaving unhealthy like 10 minutes or more before the disruption. So from a visual perspective, we could just see 5 minutes before that it will soon occur. But there are a lot of signals that all contain information. There we have a too high oxygen level already minutes before, which is telling us we are in the build-up phase. This signal already 10 minutes before has a peak that is higher than it should be. This is also telling us something is happening. This signal very obviously tells us something is wrong. And all this together, the fingerprint tells us not only the story that for us to understand as an engineer and to really figure out, I need to reduce oxygen, or I need to increase pressure, or whatever. It tells us at an early stage we are now in the build-up phase, and we should really apply countermeasures now to be able to prevent this from happening. And in the end, there are two things that can be done. One thing is it might be a one-time fix. So let's say you see the fingerprint and you just understand what's wrong, and you can just rebuild the process. You change something in the process and the problem is gone forever. This is one option. And the other option is that you have you need an ongoing protection. This is a little more, or this is just the other side. Let's assume the problem cannot just be solved once, but it is something that you have to solve during the process. As soon as the build-up phase comes up, you want to apply a countermeasure. And this is what we, This is where we then need a risk signal. So step 2 would then be for such an ongoing protection to have a risk signal. We can, with the fingerprint, just create such a risk model. Usually the AI can provide it to us. And this is now consuming all the signals from before. And it is telling us the current risk. So those orange boxes tell us, oh, the risk is now high. We should now apply a countermeasure. So we receive a warning from the risk signal. We apply a countermeasure. And then we know that we should now apply the countermeasure to lower the risk before something happens. And in the end, this is how we can avoid those recurring disruptions. So figure out the fingerprint, understand them, create such a risk sensor. And then as soon as the risk exceeds a certain threshold, we create a warning, however we want to do this, and we push the countermeasure to the operator, to the machine operator that applies the countermeasure to lower the risk again. All right, so this was the theoretically or the presentation part, and now I want to hand over to my colleague Jürgen to tell you what this looks like in a real industrial application in the paper break case.
Yeah. Thanks for the introduction. I think you have to stop sharing that I can share.
Yeah, sure. That's a valid point.
Yeah, sometimes I have my bright moments. Okay, so I hope the screen is now visible and you guys can all hear me. I'm going to quickly introduce Voith as a company. So from whom is this information coming? Then I'm going to give you some insight into the problem that we're trying to solve with AI. And then I'll show you how the solution looks in real life and what our customers are achieving by using the tools we provide. Voith as a company, I'll not bore you with that too long. We're quite a dinosaur with more than 150 years history now, present in all continents except Antarctic, and we're a traditional machine builder basically. And we're active in a couple of industries. The core industries, one of them is Voith Hydro, so electricity generation from water. And about 25% of the electricity that is used on the planet is generated on Voith turbines. And you can get everything from the huge dams down to the small hydropower plant for the river next door. We are active in paper as an OEM. So basically you can buy a full paper manufacturing line for Amazon boxes, for toilet paper, for copy paper, not so common anymore. And also here we have a huge market share on paper that is in use and daily use that is produced on Voith machines. And then the third pillar is Voith Turbo. That's more diverse. It's basically about power transmission, gearboxes for trains, ship drives, huge gearboxes for nuclear power plant, gas power plants, also more and more wind power involved. Now we're also going into hydrogen, but here we're not an OEM. We're basically only delivering the component. So the gearbox, for example, that transmits the power. And it's not gearboxes as you know them from your car. It's more the stuff that weighs a couple of tons and still needs to be super precise. So basically, almost every one of you was in touch with a Voith product today, if it was in the bus in the morning or using the shaver, but nobody knows us usually because we are behind the scenes, just delivering the machinery for a lot of applications. Just in figures, roughly 20,000 people. Last year was a record with 5 billion euros turnover, and we spend a significant share of that in R&D. And when we're talking about R&D, this is also a journey we're going together with our customers. And one very essential part of it is that we want to enable our customers to use artificial intelligence in optimizing their processes, because they usually don't have time and resources. And we, as the machinery and process supplier, we are doing that effort for them and are offering easy to use solutions for our customers to leverage the power of AI. Also for us, a quite good business nowadays. So the problem we're going to look at today is break prevention. So, and maybe to give you an insight what a paper break means, In the left-hand side, you can see the biggest paper machine on the planet that's in China, and of course it has a Voith label on it. That beast is about 660 meters long. And on the right-hand side, I tried to give you a drawing, but the drawing is so long that it goes then on in the next line. And in the cut, a bit tricky to see the red thing here that goes over all of those rolls, in this case in thermal drying, is the paper sheet. And there is events that cause this sheet to break. So you stop winding it at the end of the machine, and in worst case, you have to start threading it over all those rolls through the entire machine back to the winder until you're back in production. In this machine, that can cost up to 1.5 to 2 hours until you're back on quality. In smaller machine, that's of course faster, but paper breaks are a huge hassle for the industry. And when we look at that in figures, here we have a typical time loss distribution. So paper machines are usually around 90% OEE. The good ones reach 93, the bad ones are in the 60s, but they all have in common that you have shutdowns, you have quality losses, but roughly 25% of the time losses are caused by sheet breaks. So it has significant impact on the customer's financial result. And anything we can do there, if we can reduce the breaks for an average machine or even a smaller machine by 50%, we start to talk about hundreds of thousands of euros. On bigger machines like the one we were seeing, we talk about millions of euros that you can save when you start reducing those sheet breaks. And the project actually started as break prediction. So everybody was accepting a message from the AI. The next break is going to happen at 3:45, and the countdown is even activated. And what we had to also painfully learn during the project, that this is actually not possible because of the build-up phase that Robert was describing in the process. You can say something is happening, the risk to have a break is increasing, but you cannot give an exact timer because the time correlation of the cause and the event is not given in the paper industry, or only for very few, not very relevant break cases. So we're not trying to predict things. And if we had that counter, it would only give you a headache, but it wouldn't really help you to solve the issue. So the target is really to prevent breaks by finding out which countermeasures can help us to reduce the risk to have such a process interruption. And when we look at how paper makers are dealing with this problem today, they have a paper machine that's a bit more simple one here on the bottom, and they have cameras all along the process. And in the top, we have the camera images. And you can see here in the very early beginning of the machine, you can already see a small spot in the camera image, and this develops over the machine. At a certain point, it pops open and the sheet breaks. So what the paper maker can now say, we had a sheet break due to a piece of dirt, but we have no information at all where that piece of dirt was coming from. So it can fall in. It could be the famous bird that was flying over the web and leaving its remains on the sheet. It could be dirt washed from piping walls. So there's, I can think of, I don't know, 50 different ways of getting that piece of dirt there. And this information is not available. Of course, paper makers have the experience to deal with that kind of situations, but actually really looking at the data we're having or the information we're having, we have no information on the root cause, usually in the documentation, which brings us into a huge conflict that we're having with the paper makers because they know this world here. So they would say for this thing we're seeing, they would say we had a lump at the wire turn roll. And then on the other hand, we have the root causes here on the top. So the true thing that is happening in the process that causes this piece of dirt. And there can be different things. And for one root cause, you can also see different symptoms. So stuff you see in the camera system, in the paper machine. And what we are targeting with the project is we want to find we try to compare it with symptoms and illnesses. We are trying to find the illness in the process and to cure it instead of dealing with the symptoms, which what the paper makers are currently doing. And that's also a change management dimension that we have to take care of. And when we look at the Boolean signal that was also described, we have that in the paper industry too. So if the line is in the bottom, everything's fine, we're producing. If we have a spike in the line, then we have a sheet break. And as said, we have a lot of different root causes for the sheet breaks. and they are completely undefined in their distribution in time. So if we were able to label them, and tricky to see here, that would be root cause of fingerprint number 1, fingerprint number 7, fingerprint 3, and so on. That was a very bad day, but still in between all the ones, there was a root cause number 8. And if we look in the data we're having, then we have to say, we do not know that. It's not written down in any documentation. It's maybe somewhere hidden in the data, but this is not a label that we have for training. That's why we had some challenges for the algorithm and also in the cooperation with Vernaio. So the first thing we wanted to achieve was to enable to understand the different root causes based on the history. So we expected the engine to tell us, okay, this one is fingerprint number 1, this one was fingerprint number 1, that was number 1, and so on. So if we look at those and we look at the characteristic signals for those fingerprints, then we can understand the root cause behind problem or root cause for breaks number 1. Then the next thing we wanted to have is please tell us what are the 2s. So they are all belonging together, then the 3s, and then you can step by step understand the different things that are happening in your machine prior to breaks, so things that increase the risk to have a break. And by understanding, you can define countermeasures to eliminate. And if you have something that you can't solve permanently, then we also wanted to detect the reoccurrence in live operation. So telling us problem number 6 is now the highest break risk, and your manager has written down when 6 is coming, then you have to go out and change a draw in the machine, for example. So those were the 2 challenges that we had for the project. And another challenge actually is the available data. And if you look at the image here, we have a full paper production line from waste paper bale going in here at the end and finished paper being reeled here. And all of this is liquid processes to here, and then it starts to be more and more solid over the paper machine. And if we connect everything, we talk about 60,000 signals that we're having in there. Usually we are only recording 10 to 20,000 signals, and a signal is a temperature, a flow, a whatsoever with a resolution of typically once per second. And they are coming from various data sources, so control systems, quality control systems, sometimes camera systems. So it's not just one data source, it's many of them. To increase the fun, it's not guaranteed that they are time synced, because the benefits of a time server that you have in a network are known. Not everybody's using them, especially when IT is involved and you have a firewall to pass to get there. So it's not guaranteed that your data is time synced. We have very long and also variable process time shifts. So because there's some storage volume is in between the different process steps, it can be from waste paper bale to finished paper, it can be 2 hours, it can also be 5 hours. And this can also change over time. So it's a tricky beast to handle. And we have sometimes extreme times to a new equilibrium when you change, especially in the water systems. So the worst thing I've ever measured was 60 hours from a chemical change to everything being kind of in the new status. So all concentrations have adjusted again. Also not making it more easy for the AI. Then, as mentioned in the slide before, the main break root causes are not known, but they are also very often not measured. So if you have more dirt in the pulp, there is no dirt sensor in the pulp. You don't see that. So you somehow have to find other indicators that enable you to do the conclusion that there was dirt. And there is no exact time correlation in between root cause and break. So that was the environment we started to work with the project. And this is a trial to explain to our customers what the engine of Vernaio is doing, Avis. Basically, it generates a full-blown process model from the raw data, so no cleaning involved, no nothing. We just throw the raw data into the engine, and it understands the interactions of the signals. So each of the red dots is a signal, and I know if this is a temperature, I increase the temperature a little, I know what happens to the others, basically. And then I can start asking questions to this mesh. And one question that we're using it for is which shapes of the mesh indicate a break risk, and who are the bad guys that are pulling the mesh into the critical position. And that's then basically the fingerprint per pattern, telling us this is the signals for this fingerprint you have to look at a certain point in time. And that's where we start then to analyze. We try to get that into an application that can be easily used by any technician. So that brake prediction, mathematical calculation, voodoo part here, that's the Vernaio engine, and everything's automated. So in the wizard, it takes about 5 to 6 clicks to generate that model and to get the predictions live. Then we have a calculation time of roughly 24 hours because we use typically a year or 2 years of high resolution data. So the main time consuming step is actually transferring the data from the database to the engine. But doesn't matter. You can drink coffee, sleep, do whatever you want. Everything's happening automatically. Then the engine also identifies automatically the patterns or fingerprints, the different fingerprints. And this information is then fed to the paper maker in the front end, and they do the analysis. They understand what's going on in the process, and then they are able to define corrective actions or countermeasures. Very often it's really permanent fixes. For some we have to inform the operator in live mode. Also part of the app. Now problem number 6 is coming. That's what you have to do. Now it gets a bit more paper makish. So this is the fire police station in front of the paper machine, the last filter that you pump the pulp through. And if you could take a sheet there and it looks like this, very clean, no dark spots in there, you have a low trash rate. If you have a lot of dark spots, then you have a high trash rate going into this police station on the final filter. And with that, a low or high probability of something going through that filter. So that could be then the piece that we saw in the image previously. And any of those particles that passes the screen can cause a break, but must not cause a break. So how the hell can the algorithm understand that dirt is the critical problem here? And the truth is it doesn't, because it's not in the data. The interpretation that dirt is the problem is done by the paper maker. But it's very easy to get there because you get all required information from the engine. So you're not searching in the 10th or 20,000 signals with your domain knowledge. You're really getting a very clear guidance what to look at and where to look at to understand the different patterns. I will not read you through this. This is just for paper makers when I usually do that explanation. They wanna understand how the engine can understand that dirt is the problem. And basically it tells us, so from top to bottom we have different fingerprints, and it tells me for this fingerprint, these flows, these consistencies, and these pressures around a certain process area even, they show deviations during alarms. So during moments in time when the engine detected that something's not okay anymore. So we have a build-up phase, and the interpretation the technologist does then, we have changed the cleaning efficiency in the stock preparation. That's where we're sending more dirt to the paper machine, which increases the risk to have a break. And in this case, so this is all real examples, an optimization of a control loop that was needed to get those variations away was a permanent fix, and the problem was gone forever. And by following that process step by step, you can really go pattern by pattern, understand, define countermeasure, remove, and optimize your process in a very efficient way, because the time-consuming step to think about and to look at all 10,000 signals is done by the engine. Still, it's complex to deal with a with a project like this. So when we do this with customers, we always follow kind of a process. So we usually have a phase where we do data connection. You have firewalls, you have IT problems, all the stuff. You download historic data that you have a year of data for the model build. And the model build here is set 1 week. Sometimes the model is odd because we have to modify the signal that we're using. Sometimes it's a bit more about the settings for thresholds. When do I want to get an alarm for the single fingerprint? And then we do a thing called quick scan. So we very briefly look at the single fingerprints to try to understand, are they telling us something already? Do we know them from other machines? Not spending more than 1 hour for each single fingerprint. Then there's a priority definition. So we understand it has high impact on the brakes, and maybe we even have an idea on the countermeasure. And then for selected 1 or 2 or 3 of those fingerprints, we go into a detailed analysis that even might involve lab sampling. So that's why it's taking 1 to 2 to 3 weeks. So we really take a sample and see if there's more dirt. in the paper when we think there's more dirt. Then again, priority, countermeasure costs €0 and might get down the brakes by 50%. Then we go into an implementation phase of that one countermeasure. That can be a day for loop tuning. That can be 4 months if we have to wait for a small rebuild. And then we continuously improve the process. And I will now take you into one example where in the quick scan segment 0, so the biggest of them, one day I will understand why we start to count at 0. The problem number 1 showed a very clear correlation to changes of the paper grade that is produced. So usually a paper machine is producing one type of paper, for example, Amazon box packaging paper, but you have different weights, different colors for that box that's produced on the same machine. That's what a grade change is. And we saw in the quick scan, there's a lot of chemical dosage signals. We have dewatering at the paper machine. We have water storage systems. So basically the entire mill was somehow involved when it comes to the water. And we also had a risk characteristic. It was relatively calm for weeks. Then we had outbursts of that particular problem for some days. And also the machine was running very bad in those phases. So an initial conclusion was that the water system somehow reacts on the chemical changes during a grade change. And it sounds a bit fuzzy, but it's actually easy to digest because that's now a screenshot of the UI of the brake protect, how the app is called. And in the end, this is the fingerprint here. So this is the signals that are important to understand the problem. Of course, I deselected now a lot of them because otherwise you will be confused by the many lines that you have to look at still. But we can see here a color signal. And again, the Amazon box example, it doesn't matter what the wave inside the box is in color because you don't look at it, but the outside of the Amazon box needs to be nice and shiny on of a homogeneous color that you feel good when you get the package in the morning with your product. So they add color into the paper to make that happen. And for 30 hours, not much happened. And the red streaks are the paper brakes, and the green is when the system indicates an alarm for that particular problem. And then the color gets switched off. Then very shortly after, the alarm goes off, and we have a monster brake series with a lot of red streaks. So that's what was catching our attention with the chemical changes, and also the water systems were behaving kind of similar. And to narrow down the root cause, we have to add some more information. And that's the whitewater ash and fines content. And I will not do a paper lecture here because I can chemically explain what's happening with the color and the fines and the retention agent. But in the end, what we see, we switch the color on, that signal jumps up. So that's a characteristic pattern. We switch the color off, and pretty shortly later, this thing drops, but it doesn't go back to the original level. It takes quite a while to come to the normal, back to the normal level. And this can be seen as a detrashing phase, because while we are dosing color, some chemicals are reacting differently. We pollute the entire process. All of that is not visible in the measuring data that we're having. And when we switch the color off, the chemicals are working normally again, and then we start to collect all the dirt that we have accumulated. We form small slimy particles that can pass through final police station, fire that on the paper machine, and we get a extremely nice series of paper brakes that are labeled as lumps in the camera system. And now, as we understood what's going on, and it was very fast to understand that because we got all information pre-digested, we can think of preventing the pollution, and preventing the pollution in that case was a rebuild. And another part of the app that you can monitor the live operations of the algorithm. Longer time frame from January till May, because we had some waiting time for the rebuild. But in green again, the alarms, in red, bit hard to see the brakes. But we had basically, before that rebuild here happened, we had a lot of very long permanent alarm, and after the rebuild, we only had very short alarms, and then we introduced another countermeasure, and then the alarms were permanently gone. So we really solved the problem, and also the engine, Avis, detected that the problem was solved, even with having no information in the data on the amount of pollution that we have in the process water. And the step that really counts was we went from 2.5 to 3 brakes per day, depending on the time frame you look at, down to a completely new level with about 1.2 brakes per day. So in one step, with just one countermeasure, a 50% reduction of brakes. And that's a for a customer that was a huge financial benefit and also the reason to continue. And if you look at that over a longer period of time, that's actually from our first pilot that we did together with Vernaio. So we had the data collection phase for roughly 1 year. That was also our first cloud connection for Voith as a company in 2018. And it actually took us 1.5 or almost 1.5 years to do the crazy magic together with the colleagues from Vernaio. Because in the beginning, the engine was an idea. And after 1.5 years, it was not a dream anymore, it was working. So we took about 2 months to define our first countermeasures. And of course, the customer is also working on countermeasures. So the green arrows is when the customer implemented something to reduce the number of breaks. The red ones is the stuff that we suggested by using the application and the AI. And the big steps that brought us from an average 4 breaks per day in this machine down to now 0.8 breaks per day are coming with the artificial intelligence driven countermeasures, because they are really acting on the root cause of the breaks and not only dealing with symptoms, which is what the green arrows are doing. So it really shows the power that we have when we use the methods of artificial intelligence and apply them in the process. And you don't have to be a data scientist to do that. You just, a simple paper technologist with no mathematical background, can create the model, can understand the countermeasures, and can then follow up also the results of the implementation, all in one app and all powered by Avis. So as a summary, it is possible to leverage the treasure that is hidden in the data. You just have to ask the right questions. So in our case, it was not try to predict, so when is the next break going to happen? It was asking what is increasing the risk that a break might happen. That's completely different thing when you think in algorithms and results. And what we also figured out, you always need to have a dedicated person directly linked to the process on site that can push the analysis, but also can push the countermeasures to be implemented. Because the methods and the understanding are established, but still the industry still needs some time to really use the potential. But I think we already were able to prove that it's possible, and we have a successful product launched in the market. That's already it from my side. Also was a bit rushing to stay in time. I hope it was possible to follow. Thanks for your attention.
Thank you, Jürgen. This was indeed very, very interesting. It's always very nice for us, always again, to see how we have successful applications in various areas and industries. And this is really one really great example. All right, I will take over the screen again. Yes, and this almost concludes our webinar, at least up to the Q&A part that follows afterwards. So let me, in the end, give you a quick checklist what you need to do to avoid recurring disruptions with AI and AI-based root cause analysis. So, I mean, there are companies with different, I would say, data maturity, different digital, it's a different level of digital transformation. Anyway, the most important thing at the beginning you need to do is to collect the data, process parameters, automation data, sensor data, everything raw, and put it in some kind of data storage solution. Might be on premise, might be on cloud, doesn't really matter. Important thing is that we collect the data, because in this data is information that we probably need. We next need to define our recurring disruptions as Boolean signals, as we have seen. And we need to then identify the disruption fingerprints with self-supervised AI. As soon as we have done so, we can go on and we can understand the fingerprints. We can create countermeasures. Those countermeasures can be one-time or can be ongoing. So one time, if I have one-time fixes, then yeah, it's already, I have already benefited enough from the fingerprint. If it's ongoing, then I need to create a risk model. You can also call it a virtual risk sensor, telling you just what is the current risk of the disruption. And then in the end, you need to establish a live data connection to feed the virtual risk sensor with the relevant signals from the shop floor. And yeah, then you deploy the virtual risk sensor. You define a warning threshold. For example, you say, as soon as the risk goes over 80%, I want to be warned and I want to apply my counter measure. And then you need to make sure in the end that someone is applying this countermeasure, that the machine operator or whoever is responsible is applying the countermeasure. And yeah, that's basically the whole thing to prevent those recurring disruptions, the whole steps. All right, so thank you very much so far for your time. And now it is the time for questions. So please feel free to use our the Q&A section to just ask your questions if you have them. Some. All right, I can already see. So one question is, can a fingerprint always provide enough information? And this is, of course, a good question. So I would say in general, the question is how much information that we want is in the data. And of course, we can't know this. There might be a lot of relevant information in it or not. Basically, it's, I would say the more data we have, the better. But of course, a fingerprint is only, the AI is not doing magic. It's just finding those patterns. And of course, it's possible that you get your fingerprints, but they just don't tell, let's say, a good story because there are too many gaps in the story. And this is possible. But I would say this is also a result that you have. You might then know that you need more data. And the other thing is that you can easily try it. You can quickly just figure out, get your fingerprints and figure out if they contain enough information. And so there's no general answer to that.
Yeah, maybe as an average from the field, if we find roughly 20 fingerprints for a paper machine, there's typically 4 or 5 of them that we can't interpret because there's information missing. For the other 15, usually it's possible to have enough information with some interpretation, like that's probably more dirt. That's already not in the data, but it's possible with the domain knowledge to come to the conclusion that it must be more dirt due to this process happening.
Mm-hmm. Right, so I have another question. So how long does it take to treat a disruption? Yeah, so I would again say it differs. If we have everything in place, let's say we just we have the data, and then we can basically just put it in the AI and get the result rather quickly. So I mean, the AI itself, as Jürgen mentioned before, it can take, if you have really a lot of data, a year and a very high resolution, then it might take 24 hours, but usually it takes much less. It takes, let's say, half an hour or an hour. So this is usually what you, the calculation time until you get to such a fingerprint. And then it might already be something that hugely benefits you with a one-time fix, with a new insight or understanding. And otherwise, it might take a few rounds, I would say. Sometimes it takes a few rounds to really figure out the right question, I have to say, to really figure out the right approach for the problem itself. But after all, it should be something that can be achieved within a few days. Sometimes it might take a few weeks. Yeah, it just depends. I mean, in best case, it just takes you one day, but yeah, it's just might be the case, might be longer. So somebody is asking the question, do I need data science expertise? We have already talked about this a little bit. So Jürgen mentioned, and actually, Jürgen, I'm sure you have mathematical background. Well, I guess more than you think. I guess every engineer has some. Anyway, the thing is, data science is the part where you really, let's say, you do a lot of data preparation, and you try out different models, you feed them with data, you train them, you try different models, you try to predict something, and you pick your own methods. It's a I mean it's really a huge thing to do data science, and you really have to be very knowledgeable to do so, although there are data science tools. And in this case, our main focus was always to not require data science expertise, to really be able, I mean, the definition of the Boolean signal is basically the most the mathematical or difficult, but also important thing to do. And then what you get out is basically signals that you know as an engineer, as a process engineer, you know your signals, and it's just showing you, okay, look, you know what, look at this signal, it behaves like this, but usually it behaves like this. And so this is what I would say the interaction between you and the AI. And this means that all the work that usually you have to do in a data science is just not necessary at this point.
I think there's one more question. In which other industries and use cases have you seen working particularly well with this approach? I think you have more industries than I, because I'm mainly focused on our industries. It was more or less working everywhere.
Yeah, it is basically working in various industries. I mean, it's a fresh approach, so I can't tell you like we have like 30 industries where it's already a successful running, but we have done it in steel with the steel slopping. We have more use cases in steel, just in the melting process and in the in the rolling process. Then we have in bottle filling lines, we have disruptions like jams and bottlenecks that are very, very hard to control and to predict, since you have just this, the production line consists of many machines that all work together. And as soon as you have an error, you usually don't even know where it's originated. So this is a complexity in such a production line. So there is an application. And also, for example, in tobacco, we also have a successful application where it's about a KPI that needs to be stay over a certain level. Otherwise, the quality drops too much and the material has to be thrown away. Yeah, and actually there are some more to think about, but I would say plenty of successful applications. In the end, this approach is not bound, not restricted to certain industries. The restriction is basically the data, that we have the data, and that we have the people who are able to understand the fingerprints. And then it's a very industry agnostic, very generic approach that can work with any kind of recurring disruption. All right. So I have one last question, which is also very interesting, of course. So do we have automated countermeasures? Automated countermeasures usually means do the countermeasures have to be created by a human being, or can they be created by a person? I would say it's a huge difference. And we have those fingerprints, of course. We have this necessary step that a person has to understand the fingerprint and come up with a countermeasure. But in the future, I would imagine that it will be possible to go even a little bit further with AI and to figure out countermeasures itself. At least I could imagine that this is would work if we, let's say, talk about set points. And so let's say if a countermeasure is adjusting some set points of the process, I assume this is something that can be learned within the model by the AI, and this is something that can be then recommended by the AI. But yeah, as I said, this is something that I can imagine that this will be possible, but for now we need, yeah, well, I think we will always need a certain amount of process knowledge and just support this process a little bit more, let's say with AI-based or automated countermeasures. Okay, I don't see any more questions now. Let's give it another minute, and but then we can conclude it. All right, then. Yeah, then we can conclude it. So thank you very much for your time, for your participation, for your questions, and for for being interested and curious. And if you have any questions or want to know more about things, just feel free to contact us. Otherwise, I just wish you a great rest of the day, and thank you again for participating.